All right. In class, we discussed where functions are differentiable. We talked about corners, cusps, vertical tangents, and discontinuities, and why derivatives can't exist at those places. We also talked about how we can use our calculator to estimate numerical derivatives. But to kind of get an idea of how we can then tie these together with what we've been doing, I wanted to go through number 39 from page 115. And if we look at that, we're given a piecewise function where we use 3 minus x if x is less than 1, and ax squared plus bx if x is greater than or equal to 1. And a and b are constants. And we're asked two things. First of all, if the function is continuous for all x, what's the relationship between a and b? Meaning we need to find an equation that if we know a, we could find b, or vice versa. Well, 3 minus x is always continuous, so that piece is okay. And ax squared plus bx is a quadratic, and for that piece, that's always continuous. So the only place I need to worry about is where they join. So this is where the limits being defined makes a difference. So this is the whole idea of what we worked on last chapter with the two-sided limit must exist, the function must exist. Well, our function value says we have to use, when x equals 1, we have to use the quadratic piece. And so my y value there, if I plug in 1, is going to be a plus b. So that's not really helpful to us, so next we turn to the two-sided limit. So that means that if our function is continuous, the left-hand limit as we approach 1 must equal the right-hand limit as we approach 1. Well, if we're to the left of 1, we have to use 3 minus x. And if we're to the right of 1, we have to use the quadratic. Well, we can actually do substitution here. So if I plug in 1 for x, that's 2. And then if I plug in 1 for x here, that's a plus b. And we actually now have a relationship between a and b. Hopefully that made sense, but we just took advantage of the function must exist, but that didn't help us. Well, the two-sided limit must exist. And so we found our two-sided, that meant the left and right-hand limits had to be equal. And that actually ended up showing us that our function value is going to have to equal this as well. So for the function to be continuous, a plus b must be 2. Then we want to figure out what are a and b so that the function is continuous and differentiable. So we know that now that a plus b must equal 2, we now have to deal with the differentiable part. And specifically, again, we have to worry about when x is 1, where the pieces meet. So this is where our one-sided derivatives come into play. So in order for our function to be differentiable, at 1, the left-hand derivative must equal the right-hand derivative. So for the left-hand derivative, that means we're using the linear piece, the 3 minus x. So there's, if I plug in 1 plus h to 3 minus x, and then here's my a plus b from if x equals 1, from back at the start of the problem. And then at the right-hand piece, I have to plug 1 plus h in for x in the quadratic, and again, here's my y value when x equals 1. But we have the advantage that we know a plus b has to equal 2. So this is 2. And I'm not going to replace this yet because you're actually going to see a nice thing when we simplify the right-hand derivative. So on the left-hand derivative, 3 ends up getting canceled out because 3 minus 1 minus 2. Sorry, brain froze there. But then, so the 3 minus 1 minus 2 ends up canceling out. I distribute the negative, so I have a negative h, and then on the bottom just h. And over on the right, if I FOIL out 1 plus h and multiply it by a, I get this part. If I distribute my b, I get this, and then distributing my subtraction gives me this. Well, if you notice, the a's cancel, the b's cancel, and then I can cancel an h out of each part of what's left. And so what I now have is the left side, that limit I simplified at -1, and on the right I'm doing the limit as h approaches 0 from the right of 2a plus ah plus b. And if I go ahead and substitute in 0 for h, I get 2a plus b on the right. So I now have a second equation that relates a and b if they're differentiable. So I have a plus b has to equal 2, and that 2a plus b has to equal -1. And here I have a system of equations which I can solve. So I chose to do it with elimination. So I multiplied the top equation by -1, added them together to eliminate the b's, which means that a is -3. And if I plug -3 back into either equation and solve it for b, I get that b is 5.